All right, guys, I am back. How about you? All right, how is your day today? Um, okay, yes, it's recording. Right, yes, it's recording. Okay, let's do let's do screen sharing. Where is it? It's right here. All right, so we will start looking at something like more like physiology. This is cell physiology. So this lay the foundation. This will lay the foundation for the future organ system, because all our body are built by the cells. We have different kind of cells, all very different, but they all have very similar, the same. They are all coming from the fertilized egg. So all cells, I mean, all somatic cells, not germ cells. Germ cell has only uh, like one set of the DNA, chromosome, haploid cells. But all the somatic cells, like skin, muscle, heart, although they are neuronal cells, they are very different, but they have the exact same set of DNA chromosome. So they have common theme. So we want to learn about that here in cellular physiology. Cellular physiology have two portions. One is general cell physiology, and then we will have another topic talk about cell division, cell duplication, proliferation is a way to say it. So let's start by talking about cell. So this is a typical human cell. We have a cell, let's see. There's a pointer. All right, we have the cell nucleus. Not all cells have a nucleus. Most of cell has a nucleus. Red blood cells do not have the nucleus. A lot of like organelles, cell membrane. Okay, so here we have the different organelle nucleus. Inside nucleus, we have nucleolus. We have inside of cell, it's called intracellular space. The fluid is called, everything inside is cytoplasm. The fluid is called cytosol. Cytoplasm, and here we have the endoplasmic reticulum, rough and smooth. It doesn't show it here, but we have rough and smooth. And then on top of that, we have these little dots. They are also organelles. They are called ribosomes. Last time we talked about ribosomes. What's the function of ribosome? Translation, that's right. Its function is to provide a protein synthesis. Golgi apparatus, and here, smooth, endoplasmic reticulum, mitochondria, smooth, cell membrane. We will start by talking about the cell membrane, vesicles, and the lysosome. So we will talk all about this. I feel this very much like extension of biology, right? But it's biology in human. So to the majority of you guys, this is kind of like a review, but it's a good review. We need to build that foundation before we move on to something more human, more like human-oriented science. So cell membrane, let's start by talking about the cell membrane right here, cell membrane. We will talk about several things. First, we will talk about this structure. It's just a wall, right? Lipid bilayer, all right. But I want to first, very important concept is that this cell membrane is the same cell membrane of all these membrane. Okay, they are all the same. They are the same. They have a very exact same structure. That is this lipid bilayer. The major components in it is the phospholipid. We talked about the phospholipid already. It's a lipid, and it has two fatty acid. And this fatty acid could be, like straight, like this one here is saturated fatty acid. It could be kinked, like this one here. It's unsaturated, okay? Just a quick review that omega-3, omega-6 are essential fatty acids. And the omega-6-3, what that means? That means that that's the double bond, the location of the double bonds. So these essential fatty acids are unsaturated. So given that, is unsaturated liquid or solid in like room temperature? Unsaturated and liquid. Okay, so our cell membrane in a way is very liquidic. Okay. So this cell membrane refer to all the membrane, every membrane from the cell to different organelles. All these membranes are called cell membrane. This wall of the cell is also called plasma membrane. So it has a special term for that. That's plasma membrane. So that's right here, plasma membrane. Okay, so when people talk about cell membrane, they talk about all these membrane in different organelles. But when people talk about the plasma membrane, it's specifically talk about the membrane of the cell wall. Okay, so it's phospholipid bilayer, and in addition to that, we have the cholesterol. So as I mentioned earlier, this is very liquid because unsaturated fat are fluid and liquid. So cell membrane become very liquid, right? And to make it a little bit rigid, we have cholesterol to stabilize it. Okay. So that liquidity of the membrane has a term, is called membrane fluidity. Okay, so for example, that if we have two cells, if these two cell membrane merge, then say one has antigen on top of it, and the other they have like a red antigen. This one has a blue antigen, and then when they merge together, they have a red and a blue. If we put the antibody to it to label it, then they will label green. Okay, green and red on two sides. But give it time, this will be flowing around, and it will be evenly distributed in the membrane. So that is the membrane fluidity. Although that cholesterol can stabilize it, but cholesterol cannot prevent any of this kind of like switching and moving around. So even though it feels like it's a stable structure, stable membrane, but you must remember that everything inside of our body is all very dynamic. They are all running around all the time, okay? So they will be moving around across this membrane. So that's called the membrane fluidity. So here is some example that these two will switch and then switch and then switch. And this unsaturated will make it more fluidity. Saturated will make it more rigid. Cholesterol can stabilize it. So that's one feature of that membrane. So concept is that without the cholesterol, it's become very, very more fluid, and that's why cholesterol has some important role in our body. One of it is to stabilize the membrane. Another thing you need to know is that this membrane is lipid, so it's impermeable to a lot of things. Something we feel very common that ion, for example, sodium, potassium, they cannot move across the membrane. Okay, so this four group of substance are important to be memorized. Oh, gas. I forgot to mention gas last time when we talked about the membrane. So it's gas, O2, CO2, steroids, vitamin A, D, K, E, and water. These are permeable, can freely diffuse across the membrane. So if they can freely diffuse across the membrane, then what's the driving force of their movement? Their movement from one compartment to the other compartment, meaning that, say, okay, let me get a pen and pencil here. All right, so pen. So say this is a cell. And for this and this, they will move based on concentration gradient. Okay, if there are more, then they will the net movement will be in the cell. If they are more in here, then the net movement will be out of the cell. Okay, so for this three group, they are driven by diffusion. For this one though, let's use a different color because that is water, so that's more like blue. For water, the movement is by osmolarity. Because say water, right? Water basically almost, because water has a lot. So here we have water. Here we also have water. So water movement is based on what? So will water move in or will water move out? The water movement is based on the substance, not the water, but the concentration of those solutes. So if the solute is high, then it's very condensed, right? So water moving like this one here. A lot of thing here, so water will move in. Because here has high concentration of stuff. It's very much like a dry towel. It will suck water in it. So water osmolarity. This one has high, inside have high osmotic pressure. And here, for example, we have a lot of substance inside of the cell. It's very like nothing, but outside we have a lot of substance, right? So, so for the water movement, water will be driven out because here we have high density of stuff. So here we have high osmolarity, high osmotic pressure. So these three are driven by diffusion from high to low. Water is from low osmolarity to high osmolarity. Osmolarity equal to the mole in water divided by liquid, right? So that's molar. And if it's in the fluid, it's osmolarity, osmolar. So that's that. So these three are driven by diffusion. Water is driven by osmolarity. Let's look into the detail in the following. Here, diffusion, for example, you have a substance here. It starts to release its substance. It will gradually fill the environment. The direction of the net movement is from high concentration to low concentration. It's very much like this one here. So this substance, this includes gases, O2, CO2, steroid hormone, vitamin A, D, K, they will move across, but the net effects is from high concentration to low concentration, from high concentration to low concentration, okay? And the other is the osmosis, osmotic pressure of the water. So for the water movement, it will move to the side with more particles. Will move to dilute the side with excessive particle. So that will move, they will move to higher condensed region. So that's the osmotic pressure. So here is an example. For example, here we have a lot of salt solution, 3%, and here's empty. If salt cannot come out, let's say we put a permeable, selectively permeable membrane, so salt cannot come going out, then water will go in because water will come into the high condensed area. So here we have, inside here we have high all right, you like that, okay. Here we are, inside here we have, yes, high osmotic pressure. We don't know why it cause that. The high osmotic pressure will be here, and here is low osmotic pressure. It's here. So it will go in from the low osmotic pressure to high osmotic. So osmotic pressure is a pooling pressure. And then you will see that water will going in and it will increase that level. So here, if we compare two compartments, then if two compartments have equal, okay, if let's say compare of two solutions, two compartments, if they have equal osmotic pressure, then A is isomotic to B. If A has higher osmotic pressure, it will call A is hyperosmotic. If A has lower osmotic pressure, then A is called hypoosmotic. Osmotic pressure is a pressure to pull the water to go in, okay? And the concentration is higher concentration will have the power to pull water to go in, and that concentration is calculated by osmolarity. In one early this week, if we will have one like assignment to calculate this concentration. And then you will find that we will talk about it in our office hour, but just very briefly, you will find that there are several ways to quantify concentration. We can quantify concentration as we can quantify the concentration as, for example, gram per decimoliter, right? For example, that we can say that how many gram of salt in the decimoliter. Decimoliter equal to 100 milliliter, right? So that's gram per 100 milliliter. We can do concentration as it. We can also do concentration as the percentage. Okay? Say gram per gram. So solute and solutes and the solution, right? Say 1 gram of salt in the entire salty water, gram per gram percentage. So we can do that. We can also do osmolarity, so it could be the molar. That's mole per liter, right? So there are different ways to quantify concentration. So this concentration can be quantified in different way. And the way that water is driven is by the concentration defined by the osmolarity, defined by this one here, okay? So another very important term is tonicity. Tonicity is almost equivalent to the osmolarity, but tonicity is a term when we talk about cells. It's more like a narrowing defined for cells. Osmolarity is common term for two solution. Tonicity, we are talking about when cells in a fluid. So for example, that here we put red blood cells. Here we have red blood cells. If we put into the solution, that cells doesn't change its shape, then we call this solution is an isotonic solution. It means that the net fluid of water movement, the net movement of the fluid is equivalent inside and outside. It's because that inside of cell, the solution, the osmolarity is equal to the osmolarity outside of cells. What's the osmolarity of the cell? This term you must keep in mind. That osmolarity is because osmolarity in a red blood cell equal to osmolarity in the plasma. That's why the red blood cell will feel very comfortable in our blood. And the osmolarity in the blood is equal, almost equal to the osmolarity in our body fluid. That's why that our blood is not easily leaked around. Okay, that make it like very stable. That's why we don't swell. I mean, if the person, if you see this, we have a very like body shape, right? Keep it like a good shape. But if the person start to appear swelling, then you will know that some of this plasma fluid filter out of the blood vessel into the interstitium, into the extracellular space. And that is usually driven by the tonicity become disturbed, okay? So that's osmolarity in the red blood cell. This number is very typical. It's very important. When you inject solution into the body, you must match that osmolarity. So the osmolarity in the red blood cell is 300 milli osmol. It's also commonly seen as 300 MOSM, okay, MOSM, milliosmol. 300. This is equal to 0.3 osmol. Okay, so that's the common osmolarity. So your plasma should match that. Your red blood cell is that. Your cells all have the same, very much the same osmolarity. So this number is very typical. When we inject the saline, normal saline is very simple, like the very cheap, simplest form of the solution we can inject into the vessel when the person have a hemorrhage, lost a lot of fluid. We can have the person to drink water to replenish that, like swelling. You know, if the person exercises swell a lot, we can then drink water. Drinking water will, even though it's plant fluid, in our body, when it reaches to our body, there are a lot of process to make it become 300 milliosmol. But if you do only inject, if you directly inject into the vessel, you better provide something 300 milliosmol. And so if we think about that NaCl, if we just inject NaCl, okay, very simple one, per liter, we want to inject it into the vein to replenish the lost fluid. The way to inject that is, this fluid is called the normal saline, okay? And the concentration of the normal saline is typically 0.9%. Sorry, 0.9%, which is equal to 0.99 gram per 100 milliliter. And if we do, you know, in your conversion assignment, you will find that this 0.9% of the normal saline is essentially the same as 300 milliosmol, because that's the concentration when we inject. We won't cause any disturbance in our red blood cells. Right. So if the cell is in the environment that has equal osmolarity, then this solution is called high isotonicity. Okay, if it's in the solution, let's say this one here, fluid's going out, right? So when fluid's going out, the cell becomes shrinked. Okay, and then we will have this is hypertonic solution, because it has higher concentration, hypertonic solution. And then our cell will feel uncomfortable. A lot of fluid going out, the cell will shrink. In contrast, if the cell start to absorb a lot of fluids coming in, that means outside has low concentration, has low hypotonicity. This one will be hypotonicity. So the solution, if the cell remain the same shape, is called isotonic. If the cell, if the water coming into the cell, meaning that outside has low concentration, is called hypotonic solution. Then this water going in, cell will swell or cell will start to break apart. It's called hemolyzed. In contrast, if the water coming into the solution, it means that outside has high density of this solution and its hypertonicity. So that's that. You probably will see this one in kind of like a lab. So you will know that just by, in a real lab, we will see this underneath a microscopy. So you will know that when we will put some red blood cells in the solution, and then we see that either swelling or shrink. and to decide whether the solution is hypertonic or hypotonic. So here is that if the red blood cells is in isotonic solution, what's the concentration of this one here? This is 300 milliosmol OSM, okay. And this one has hypertonic because too much water going in, and one day this cell membrane is phospholipid, it got burst. You can see burst, and then this cell hemolyzed. Or water going out to make it shrink, hypertonic solution. So that's the cell and intracellular solution and extracellular solution. In our body, we have basically the similar situation that our cell in the cell is called intracellular solution, intracellular space. And this intracellular space also is called, in intracellular space, this fluid is called cytosol. And we sometimes hear the term cytoplasm. Cytoplasm is cytosol plus organelles, everything inside of the cell. Organelles are intracellular structures. We will learn about that today. And outside of cells are extracellular space. This extracellular space include some major ones are interstitial fluid. So it's any fluid outside of cell, but not in the blood vessel. We also have plasma. This is a fluid in the blood vessel outside of the red blood cell, but this is in the compartment of the cardiovascular system. Cerebrospinal fluid is also fluid outside of the cell, but this fluid is in the compartment of the nervous system. We also have some more, for example, fluid in the eye, intravitreal space. Those space also have fluid. These are also extracellular, and they are in the compartment of the eyeball, in the eyeball. So, but those are comparatively very small amount of fluid. So in the body that we can classify the fluid in the intracellular fluid and extracellular fluid. You don't need to remember a number, you just need to know that extracellular are those outside of cells. Interstitial is extracellular fluid. Plasma is extracellular fluid. So that's something you need to must know, that plasma is not intracellular, it's extracellular. Interstitial is also extracellular fluid, okay? So, all right, so that is the membrane. The major portion of the membrane is a lipid, but membrane also anchor on some of this protein. Remember that protein is tool. We make these proteins as tool to conduct a lot of works. So we put this protein on the membrane to do a lot of works. Okay, so in the membrane, say this is a membrane, we can have the protein to act as the transporter. So one particle binds on it, move it to the other direction. We can make it as the receptor. So this one, for example, is an insulin, can bind on it, cause the events inside of the cell. So that's a receptor. This one is a protein. Enzyme can convert from, say, sucrose to glucose and fructose. So this is enzyme, can act as an anchor, okay? To anchor the say this one is extracellular matrix, like collagen, or the intracellular cytoskeleton. Or it can be the channel. Channel could be something like this one here. Let me draw it here. So we can have a channel like this one here, right? This one here, so substance, say sodium, can go in. Okay, for example, another channel is like channel like this, potassium can go out. So this channel, without that channel, can sodium pass across the cell membrane? Can sodium pass across the cell membrane? No, because sodium is not lipid soluble stuff. They are water soluble stuff. So they need to have a channel to open a window for them or door for them to go in and out. So we have a lot of, so in the cell membrane is the foundation. So cell membrane foundation, and and on top of that, we can anchor or attach many different kind of protein. So this one, so protein to it. So this is protein. Sorry, protein. And this is lipid. So in this lipid membrane, we can anchor a lot of protein to it. And these proteins serve a lot of functions. The major function is to provide a channel so stuff can go in and out, okay, can diffuse across. Or we can have the pump. So we can have the pump. So we can have, here is a pump, okay. So this is a pump. So pump can pump things in and out. Can be diffused or can be pumped. Okay, so we can pump. Or here, channel, if it's a channel, it basically allows a diffusion to diffuse across. But all these are proteins. All these are proteins. So now we have, earlier we talked about that, we have four different types of organic molecule: lipid, protein, carbohydrate, nucleic acid, okay? And here we see that lipid, protein. Later we'll know that we can also have some carbohydrates. Carbohydrate usually doesn't provide a function. Protein does provide a function. Lipid is kind of like a boundary, a structure basis. But the protein, carbohydrate can bind to it to act as a decoration. And that is very important because some decoration can modify the function. Some decoration can be used for the identification of different cells. So they can be used to be recognized as different cells or different. So this protein plus carbohydrates, this carbohydrates plus protein or carbohydrates plus lipids can be used as an antigen. And that can be recognized by antibody or by some other cells. So these are the protein. Protein function can be receptor, can be the channel, can be the carrier, enzyme, anchor, recognition proteins, identifier, okay? These identifier usually decorated with the carbohydrates. So here, without, say this one is without any protein, stuffs can diffuse. This diffuse across. Only 4 groups of the substance can diffuse. Gases, okay, O2, CO2, they are very important. These are lipid soluble. Water is driven by the osmosis. Steroids, hormone, and the vitamin A, DKE can diffuse across. Others are allowed, like glucose, right? We need glucose, sodium, potassium, ions. We all need that. And a lot of protein, like insulin, like some other things, they cannot. But insulin, for example, and then they will need to have this channel to let the water-soluble substance to go through. And we also have this water-soluble substance, but when they diffuse, they move from high concentration to low concentration. We can also have the ATP, use ATP to pump it from low concentration to high concentration. So protein can serve as the channel or can serve as the pump to move substance from one location to the other. If its channel is moving from high concentration to low concentration, if it's an active transport, a pump, it will move from low concentration to high concentration, and that movement require energy, ATP. So let's first look at the facility. So these two are diffusion. This one doesn't require any channel. This one requires channel. This one requires channel. It's called facilitated diffusion. Facilitated diffusion is a type of passive transport. It doesn't require ATP. It moves from high concentration down their concentration gradient, okay, to a low concentration. Two categories, two group of the protein can do that. One is called channel, the other one is called carriers. Channels can open to both sides, so it's always open. Carrier moving from one to the other, but it's always moving from the high concentration to low concentration. So this is a example that protein to form a channel. So here you can see that in the beginning, the protein is primary structure, linear structure. Then it can fold it up as alpha helix to form the secondary structure. And then they can fold together, like this one here, to fold together to form like a tertiary structure. And then you can form this channel anchored into the cell membrane. This channel can be gated or can be non-gated. Non-gated one is also called a leakage. So basically it's open there, it's not gated. So anytime, anywhere, substance can diffuse across by concentration gradient. Another one is gated. Gated means that it's commonly closed unless it's opened by one of the two events. So it could be that, so this gated can be opened by either by the voltage, if the environment has the voltage change. If the cell is excited, for example, is excited, then the voltage across the cell membrane can trigger it to open or close. Another type is called ligand gated, means that there is a chemical to bind on it to make it open. So it could be ligand gated, or ligand can also be bind on it to close it. Okay, So this ligand can be used as a target for drug development. Like if the person is lack of some ligand, then its ion, its channel open and close will be abnormal. So we can provide some drug to mimic that ligand to open or close that channel. So that's the channel. And this is a carrier. A common carrier, a very typical carrier is glucose. So glucose binds on it and moves it across. Glucose cannot transport across the plasma membrane. So it has to go through something. And usually it doesn't go through a channel, but it can go through a carrier. Sometimes we call this one a transporter. So that's the facilitated diffusion. Another type of the transport is an active transport. This one will require ATP, and this one can move substance from low concentration to high concentration. And so this one is also called a pump. A typical pump is sodium potassium exchanger or sodium potassium ATPase right here. A typical one is this one here. Sodium potassium ATPase. And this one works too. So this is the cell, and this pump, say right here. It will pump 3 sodium out and the pump 2 potassium in. Okay. So that's that sodium potassium ATPase. All right. Any questions? So here is a summary that to move substance across the membrane, we have the passive transport, which doesn't require ATP. And then with this one, we have 3 mechanisms. One is a simple diffusion. For a simple diffusion, only those can move across the cell membrane freely can do that. So they are the gases, steroids, hormone, vitamin A, D, K, E, and the water. Osmosis is the water movement. And for those who cannot freely move across a cell membrane, then we need to open a channel for them or carrier. And this is called facilitated diffusion. They are also diffusion. They are also passive transport, but they require a channel to let them go through it. So that's passive. And another one is called active transport. And the second active transport. This one requires ATP to move them from low concentration to high concentration environment. And the one example of the active transport is the sodium, potassium, ATPase. Let me pause it very quickly. I want to drink water, and I also want to, and I'll be back. Okay, give me a second.